The method of sections is one way to analyze trusses. First of all, before we use the method of sections, we have to make sure that what we're analyzing is a truss or a frame. Trusses and frames are groupings of bodies connected together. They usually support something. Examples would be a bridge or a roof truss. They do not allow relative motion between their members. So if we look at these pictures, these are all examples of different types of trusses you would see in a roof or in a bridge structure. Another example of a truss would be, or frame would be, this particular part of this crane. This triangle is a frame. Now you will notice, however, that it's hinged here and here. Those 2 points are pivots. Therefore, the whole object is not a frame or truss. It would be machined, and we'd have to deal with it differently. But this triangular piece can be considered a frame. We can use this method of sections on it. Likewise, if we look at a bicycle, the bicycle frame also does not allow relative motion between its members, and we could use the method of sections to analyze it. Before I go into the procedure, we need to talk about the assumptions. The first assumption for this particular method is that all the members are straight. The second is that they're fastened together by smooth pins, or that the joint locations can be represented by smooth pins. An example of that would be a gusset plate. Third assumption is that all loads and reactions occur at the pins, at the points of connection between each member. The next assumption is that the weight of the members is very small when compared to the overall load that they're supporting, so it can be neglected. For a roof truss, for example, the individual members would be made out of wood in most cases, and compared to the actual weight of the roof, the weight of the members is fairly low. Also, we are assuming that the trusses are composed entirely of two-force members. Two-force members are objects that have only two forces acting on them. So for example, if we've got this particular object, there's a force there and a force there. Two forces acting on that object, both trying to pull it apart. When we analyze these problems, no longer should you include a direction. So don't include an angle or a slope triangle. Instead, we use T for tension and C for compression. Tension is when an object is being pulled apart. Compression is when it's being squeezed together. When analyzing trusses and frames, there are two methods we can use. We could use the method of joints or the method of sections. In this particular case, we're going to use the method of sections. You would choose the method of sections over the method of joints because the method of sections is most useful when not all of the forces are desired. So when we only want to look at forces in some of the members, not every single member. If you want to know the force in every single member in a truss or a frame, you would definitely use the method of joints. The other thing that's nice about the method of sections is that it allows you to come to an independent solution. The method of joints is dependent. The method of sections is independent. So first, we construct a diagram of the truss. Then we locate and identify all members of interest. I usually locate those by putting a little circle around the member or putting a hash mark through it. Then we make a cutting plane. We sketch a cutting plane. There are certain rules about the cutting plane, however. First of all, the cutting plane always has to cut some of the members, otherwise it doesn't do anything. It needs to cut at least one member of interest. It should have no more than 3 unknowns, and the cutting plane has to make a continuous line and not pass through any member more than once. So examples. The red ones here are not okay, the blue ones down at the bottom are okay. In this particular case, this cutting plane is not okay because it cuts this member more than one time. This cutting plane is not acceptable because it's discontinuous. This cutting plane is not okay because the truss is not completely sectioned. This cutting plane is perfectly acceptable because 3 members are cut. This one is also perfectly acceptable. Once again, 3 members are cut. Now these two at the bottom are both okay for cutting planes. However, these would produce more than 3 unknowns unless you knew something about the truss already. So you could solve this assuming that you had no more than 3 unknowns with either of these two at the bottom. After we sketch our cutting plane, we then determine the support reactions if they're required, and we use the entire truss or frame to solve for the support reactions. After that, we construct a free body diagram of one of the sections, and we solve that using static equilibrium. We'll apply static equilibrium to forces in the x direction, we'll apply static equilibrium to forces in the y direction, and we'll apply static equilibrium to moments about different points. We'll repeat those 2 steps until all of the unknowns are found. So you may have to construct more than one free body diagram. You might have to construct 3 free body diagrams for a problem. And then finally, you will report the answers, magnitude and mode. Magnitude is just the amount of force, and then mode is either tension or compression. So don't include positive and negative signs, don't include arrows. You would say, for example, 50 kilonewtons in compression. That's the way you would report the answer. Here we'll demonstrate the use of the method of sections on a truss. We are looking for the force in CF, GF, and CD. The first step is to draw a free body diagram of the entire truss. After making our sign convention and labeling the forces and distances, the next step is to apply our support reactions. So over here at point A, we had a pin. A pin or hinge is going to produce 2 unknowns, an X and a Y. Over here at point E, we had a rocker. A rocker does exactly the same thing as a roller. It produces 1 unknown, a force perpendicular to the surface at the point of contact. Now step number 2 is called a global path to solution. You're no longer required to do an equilibrium analysis, although you may continue to do so if you still choose. What we're going to use instead is called a global path to solution. Now before I actually fill in all the details of the global path to solution, this just basically says what I'm going to do in what order. I want to come back to the diagram and figure out what the unknowns are that I need to solve for. So as I said, I like to put little circles on the members in question. So the original problem statement said I need to figure out what the force was in CF and GF and in CD. So that's those 3 members. So if I make a cutting plane that cuts all of those 3 members, it would look like this. And I'll label it cutting plane AA. Now when I section the truss, I will use one side or the other. And many times what I do personally is I try to figure out which side of the truss is going to be easier. So if I cut off and use the left side here, I'll have to solve for both F5 and F4. I'll have to use both those support reactions to solve for this side. If I cut off the right side, I'll only have to use F3. So I'm going to choose the right side because there's fewer things I'm going to have to solve for, but I will need to solve for support reactions. The first step is to solve for support reactions. The second step is to take this free body diagram, cut it apart, and draw a new free body diagram of just the right side. After that, I'm going to solve for CD, then I will solve for GF, and I will finish by solving for CF. Now really the order in which you do those, it could be any order, but you need to solve for the support reactions first in this particular problem. I always write solving for support reactions, plural, even if I'm only going to solve for one, and that's perfectly acceptable. In this case, since we're using the right side, we only need to solve for F3. Looking at this free body diagram, you'll see that F4 and F5 both intersect at point A. So if we sum moments at point A, that'll cancel out both F4 and F5. I know F1, I know F2, so my only unknown there will be F3. So I've got my statement of static equilibrium, and then I've got my zero statement. If you want to continue and write plus F4 times D perpendicular and plus F5 times D perpendicular and then cross them out, that's fine. But if you see that they equal 0, they don't produce any moment, you may leave them off. F1 is going to produce negative rotation around A, and its perpendicular distance is C plus D. Likewise, F2 will produce negative rotation, and its perpendicular distance is C plus D plus E. F3 will produce positive rotation around point A, and its perpendicular distance is C plus D plus E plus F. Solving that equation for F3, and now we can plug the numbers in. And we'll find that F3 equals a positive 4.75 kilonewtons. It's important that you keep in mind the significance of this positive sign. That means I assumed this correctly, so when I redraw my free body diagram, I'm going to draw F3 going up. If this would have been a negative, when I redraw the free body diagram of this section, I would have to draw F3 going down. Now look carefully at what I've done. I've taken the truss and cut off the left side of it so that all we have is the right side, triangle DEF. F2 is applied to triangle DEF, and so is F3. Notice that F3 is now known. Also notice that all three of the pieces that I cut now result in three forces. I cut member GF, so where I cut that, I now have force GF. I cut member CF, so in its place I will have force CF. I also cut member CD, so in its place I will have force CD. You must assume the unknown forces in tension when you do this problem, which means they are pulling on the object you have drawn. So GF is pulling on point F, CF is pulling on point F, CD is pulling on point C. That is a requirement. How do we solve this particular diagram? Well, I would begin by extending the lines of action of all the unknowns. After extending all the lines of action unknowns, we want to label their points of intersection. This point right here is point F. This point over here was point C. And this point over here I'm going to call point I. Now before we go any further, there's a couple additional distances we're going to need. Distance E is the distance from point C to point D that was already given. I will also need to know this distance here, the horizontal distance from E to I will call that distance G. There are also some angles that would be beneficial to know. Alpha is 45 degrees, and I will need to solve for angle beta. Now I'm going to do all these calculations in an OxComp. We can find beta using the inverse tangent of 2 divided by 4. Since we have similar triangles here, there's a triangle formed by point G, point F, and this point over here. That triangle is 4 meters at the base and 2 meters tall. So beta equals 26.5651. In order to find distance G, I have a triangle that's 4 meters tall and 8 meters at the base with an angle of beta. So I can say the tangent of beta equals A plus B divided by E plus F plus G. Solving for G will tell us that G is 4 meters exactly. So according to my global path to solution, I said I was first going to solve for force CD right here. There's a couple ways we could solve for force CD. We can't use some of the forces in the y direction because CD is horizontal. So we could try to use some of the forces in the x direction. But notice, CD has an x component, CF has an x component, and GF also has an x component, so that's not going to work out. Instead, we're going to have to use moments. And if we look at CF and GF, they both intersect at point F, so they won't have any moment at point F. CD, however, does have a distance to point F. So we can solve for CD, applying static equilibrium to moments with respect to point F. So start with our statement of static equilibrium. Then we're going to write out our zero statement. GF and CF both go through point F, and so they're going to produce 0 moments. That's the nice part about labeling your forces like this. If we sum moments at F, we know that any force with the letter F in it is not going to produce a moment. Also looking, F2 passes through point F. It's not going to produce any rotation either. F3 is going to produce a positive moment, and its perpendicular distance is F. CD is going to produce a negative moment, and its perpendicular distance is B. Solving for CD, and now we can plug our numbers in. And we see that CD is a positive 4.75 kilonewtons. Now, since our answers are supposed to be reported with mode, the very next line should be CD equals 4.750 kilonewtons in its mode. In this case, positive is tension. This will only work out this way if you assume all your forces in tension to begin with. Now, my next step, I said I was going to solve for GF. Now, if we're looking for a place where GF is the only unknown, we'll notice that CD and CF both intersect at point C. So when we sum moments at point C, they cancel out, and GF will be the only unknown then. Looking back, we see that CD and CF both go through point C. F2 has a perpendicular distance, F3 has a perpendicular distance, and GF also has a perpendicular distance. So all of those things will produce moments. F2 is going to produce a negative rotation around point C, and its perpendicular distance is E. F3 is going to produce a positive rotation around point C, and its perpendicular distance is E plus F. Now, since I don't know the perpendicular distance of GF, I'm going to break it into its x and y components. Its x component is going to produce positive rotation around point C, and the value of its x component is cosine beta times GF, and its x component starts right here at point F, so it is B away. Its y component also will produce positive rotation. The value of the y component is sine beta times GF. Its y component is located right here, and so it is E distance away. Now we can bring both of these terms with GF over to one side, and now we can solve for GF. Now we can plug our numbers in, and we'll find that GF equals a negative 4.845 kilonewtons. Since it's negative, it means it's going in the opposite direction that we have drawn it, which means that GF is 4.845 kilonewtons in compression. The last force I said I was going to solve for was CF, which is right here. To solve for CF, we need to figure out where GF and CD intersect, and if we draw the lines of action, you see that CD and GF intersect at point I. So we start with our assumption of static equilibrium and our zero statement. Notice I haven't written down CD or GF because they both cancel out. F2 is going to produce positive rotation around point I, and F2's perpendicular distance is F plus G. F3 is going to produce negative rotation around point I, and its perpendicular distance is G. Since CF is acting at an angle, I'm going to break it into its x and y components. CF's x component would be right here acting at point F, and it would be producing positive rotation. The value of CFX is cosine alpha times CF, and its perpendicular distance for the x component is B. CF's y component would be right here, and it would be causing this type of rotation, which is also positive. The value of CF's y component is sine alpha times CF, and CFY would be right here. It would have the same perpendicular distance as F2, which is F plus G. Grouping like terms together and solving for CF yields this. Plugging the numbers in, and we'll find that CF equals a negative 0.5893 kilonewtons. So that is 0.5893 kilonewtons in compression. And all of the answers, both magnitude and mode, go inside the answer box at the end of the problem.